All right, thank you, friends. Thank you for joining us. Just press record on this adult forum on the 20th of November. We have Mary with us. I think before she starts, she's gonna give a little introduction about herself, I know. But also, for those of you who are a little bit late, I was chatting with Debbie this week. I said, Debbie, I don't think I'm competent enough to facilitate the conversation. I said, why don't you do that? And she said, oh, I have too much on my plate. And I said, and I told her, and she has a lot on her plates. So, and she said, let me ask her husband. And let me ask my husband. And whenever, I mean, it was probably a few minutes later, she calls me and said, yeah, my husband can, really help the conversation going, keep the conversation until 1. So before I turn it over to Mary, I don't know, Bill, if you have anything to say. Yeah.
No, not yet. I'm really interested in hearing Mary's presentation. And of course, my wife is quite good at lassoing and roping everybody into doing things. So it'll be fun to hear this.
Yeah. So thank you, everyone. Thank you, Mary. I turn the floor to you.
Yeah. Okay. So before I get started, I just want to preface this by saying that I wasn't really sure what the format of this was. So I went ahead and pulled together basically like a 40-minute presentation. So that should, but I'd love to stop and answer questions when they come up. And hopefully but we can also answer questions at the end. And yeah, I just hope that, this is interesting for people. So I'm going to go ahead and share my screen. Okay. All right. So welcome to Seasonal Outlooks and Beyond. So a little bit about me. So I'm from Maryland. I grew up with strong values, like a strong feeling of stewardship, which I know is a word that which is a word that I know we really like here at St. Peter's. I went to, I think somebody's mic is on. Kind of hear an echo. Oh, there, it's gone. I went to St. Mary's College of Maryland, which is right on the St. Mary's River. So beautiful place, lots of nature all around. And I did a summer internship there, modeling oyster dependence on salt in the Chesapeake Bay. And that's kind of what started me down the path towards climate and, interdisciplinary studies. So I graduated from St. Mary's in spring 2019 with a bachelor's in applied physics. And then I went into the climate dynamics program at George Mason. I just did my thesis for the climate science master's last fall. And I'm hoping to defend my dissertation proposal this spring and then graduate with my PhD in spring of 2024. So all that to say is that I'm at the start of my climate science career, but I've learned some stuff and I'm happy to share it with you. We, in our field, we talk about telling stories as a form of scientific communication. So I've kind of structured this as sort of a story. So this is a story about how we think about climate, as told in 3 parts: what was, what is, and what is yet to come. We think it's the past. In the beginning, there was chaos. So chaos and weather are inextricably linked. In 1962, Edward Lorenz was feeling pretty lazy one day, and he accidentally created the field of chaos. So he had a computer, a computer that he was running a toy weather model on, one of the very first of its kind. And I say a toy because that's what it was. He would have people coming in from all over his department just to poke at his model and go, oh, but what if you did this? What if you did that? Oh, look at it go. It's changing the weather. And it would print out a sheet, right, full of symbols representing how the wind changed or how the temperature changed at different latitudes. And he liked to start it all at the same time with the same wind and temperature and pressure conditions, right, every single time. One day, he started his model halfway through the simulation he was running, instead of at the beginning. So he looked at his readout sheet from where he had stopped last night, and he was like, oh, okay, these are the different values that that we were at last night. So I'm just going to type them in here, and I'm going to go get some coffee. And he went away and he came back, and it was a completely different simulation. He was like, wow, what happened there? Well, so the computer had stored 3 more digits than it. Oh, what? Stop. The computer had stored 3 more digits than it had printed out onto that sheet, rounding it to the nearest thousandths place. And this small difference on the order of 0.0002 was enough to create a completely different scenario. And this eventually led him to what we call the butterfly effect, right? Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? It's this idea that tiny changes in initial conditions can create very different results. So Lorenz created a simple model to play with this idea that small changes in initial conditions create very different results. So we see a colorized version of it on the left here, where he took a model and he ran it repeatedly with slightly different conditions at the start, and no path is ever repeated. But as you can tell by the wings of the butterfly, there still exists order in the chaos. So how does this apply to weather? Well, we're limited. As Lawrence discovered, right, machines can present inaccurate data. And no matter how sensitive or how precise our instruments are, there will always be uncertainty. And this uncertainty is what creates the 10-day forecasting limit that you see on your phones or on the Weather Channel. But the order present in the chaos, the butterfly wings, is what gives us predictive power. So how do we find the order? Well, rather than creating one forecast, we create many. So we take a climate model and we run a simulation using the measured conditions, and we call that our control. And then we randomly add or subtract a very small number to the measured conditions and then run it again. That creates our ensemble number. So on the right here would be each one of these blue lines would be an individual model projection or ensemble number. So in the end, we have many ensemble members, which create a wide spread of possible forecasts from slightly different initial conditions. And that's what we would call the projection uncertainty. And so it's likely that the true forecast is within the spread. And so a lot of the time when you're talking about forecasts, people will say, okay, this is the ensemble average. This is the average over all of the different runs that we've made. So this is the average forecast. So that leads us to talk about present. So how good are our predictions anyway, given that we have this level of uncertainty? Well, it depends really on what we're trying to predict. So if we take the Earth system as a whole, right, we can think about it as existing in 3 different parts, technically. If you want to get, into the real if you want to get really nitpicky, there's also the cryosphere, the ice sheets, and at the North and South Pole. But like for our purposes, we've got the atmosphere, land, and the ocean. So the atmosphere has a high predictability. This is a predictability scale versus time scale. So atmosphere has a pretty high predictability until about 7 days. And the land has relatively good predictability between 7 to 30 days. And we might not know what the ocean is doing this month, but we can guess pretty well what it's doing around 3 months from now. But looking solely at the atmosphere, because that's where all of the weather is happening that we're interested in, right? Specific weather has a high scale of until about 10 days, which is that limit I was talking about earlier. So what we've got on the right here is prediction skill versus time, prediction lead time. So we can see weather events here are pretty well predicted until, well, at 2 weeks, there's in essence no prediction skill. And seasonal statistics have about 30% skill starting around 3 months. And this is due in part to the ocean predictability, right? And that leaves us with a gap between the 2 weeks to 1 month area. And that's where we would predict tropical cyclone activity, heat waves, storm tracks, severe weather threats, that sort of thing. But we can still make reasonable predictions out, on the other sides of the gap, so about weather and climate beyond the gap. So just very fast, weather versus climate. I know some people know this, but some people might not. So with weather, it's what you see is what you get. That's your weather. Climate is the statistics of weather over time. So for today, if you look out your windows, it's sunny. There was some windy conditions predicted for around 10 a.m. High temperature 36 degrees Fahrenheit and a low of 22 degrees Fahrenheit. Today's climate in DC has an average high temperature of 57 degrees Fahrenheit and a average low of 40 degrees Fahrenheit. So today is actually quite a bit colder than we would normally expect for this time of year, based on the last 30 years. Average precipitation today in the climate is about 0.1 inches. And just for fun, I wrote down the daily record highs and low temperatures. So we're almost at a record-breaking low, actually. Yeah, so I was like, oh, that's weird. Why are we so much lower than the average? And so I went and I was like, what's going on in the weather today? And today is this week really there's been an Arctic outbreak, which will be a more common occurrence as the global patterns change due to global warming. Okay, so going back to our prediction skill, seasonal outlooks. So predictions about these are predictions about weather statistics made about 3 months ahead of time for the upcoming season. And as I said, their predictive power comes mostly from ocean temperatures. They predict seasonal outlooks predict El Nino phase, temperature and precipitation anomalies, and even hurricane frequency. And anomalies refer to how far from the average climate over the last several decades the value is. So why do we do seasonal outlooks? So I just went through and I wrote down a couple of points. So for temperature, energy companies want to know how much energy people will need in the next 3 months. So the seasonal outlooks with respect to temperature can say it can help them figure out when there will be a high demand for energy, such as when it's really hot or when it's really cold, and best time to schedule maintenance procedures. And forestry managers are looking for increased chances for warmer than usual weather, and to see if they'll need to take extra measures to prepare for wildfires. Managers in agricultural industries look for if temperatures are likely to be warmer or cooler than usual, and that can help optimize food production. Precipitation seasonal outlooks. Water managers, farmers, and forestry officials make decisions about water resources, irrigation, firefighting resources. Flood forecasters like to know as early as possible if an area is likely to receive more precipitation than usual. And then drought. If a drought is likely to develop in a region, then farmers and ranchers may decide to delay planting or plant a drought-resistant crop, or even stockpile food and water for livestock. Forestry officials may choose to hire additional firefighters and secure equipment to be ready to fight wildfires, and water managers may consider instituting water restrictions. If drought is likely to improve or end, then ranchers may choose to begin using stockpiled resources, or farmers may choose crops that require adequate moisture. So this is the outlook for this upcoming winter, December through February, basically. So probability is calculated by looking at the ensemble spread of the forecast. So we're looking specifically at what percentage of the spread is below normal or above normal for the temperature. So we've got below probability, we've got probability of below normal in blue. The darker the blue, the more likely, and above normal temperatures in red. The darker the red, the more likely. So as an example, Hawaii is very likely to have hotter than normal temperatures this winter. We can see that the south and east coast are leaning towards higher than normal temperatures. The northwest is leaning towards lower than normal temperatures. But of course, the limit with these outlooks is that you can't say with certainty how much hotter or colder than average, just that temperatures will likely be hotter or colder. For precipitation, below normal precipitation is given by Brown. And again, the darker the shading, the more likely the precipitation is below normal. And above normal precipitation is in blue. So we can see in the south, south is leaning towards a drier season overall, and southern Texas in particular is is more likely to have a drier season. The Northwest and Great Lakes regions are leaning towards a wetter winter, with Hawaii more likely to have a wetter winter than normal. And then our drought outlook. So this there is no drought in the white areas. Drought is developing in the yellow areas. There's currently a drought and it will continue or worsen in brown areas and improve in kind of beige areas and end in green areas. Drought continues or worsens in the southwest and central US this winter. There are some places where drought is improving or ending in the Northwest. There's a developing drought in the Southeast. But the precipitation this winter in Hawaii should help either improve or end their drought conditions. So that's good. So to sum up this section, after 10 days, skill and prediction dropped significantly. However, we are still able to make useful predictions a month or even a season in advance. But what about beyond the season? What do we think is coming not a year from now, but 50 years from now? So looking towards the future, how do we predict the climate in 100 years? The same way that we make weather forecasts and seasonal outlooks using climate models. But given the long time scale, how can we be sure that what we're predicting is what will happen? I mean, basically, we can't be absolutely sure. The first climate model didn't even exist 100 years ago. There's no precedent for predicting accurately or inaccurately what will come in 100 years. But even then, there are a few things that we can be pretty sure about. One of them is the relationship between global temperature and carbon dioxide. The relationship between increased carbon dioxide in the atmosphere and increased temperature is well founded. So physically, right, if you take a glass tank full of carbon dioxide and you put it under direct sunlight, and right next to it you take a glass tank full of regular atmosphere and you put that in direct sunlight, you wait a few, you let them sit and wait a few hours, and then you go back and you measure the temperature. The glass tank with carbon dioxide will be hotter than the glass tank full of regular atmosphere. Observationally, this is seen in the correlation between the Mauna Loa carbon record and the global mean temperature. And in our climactic past, with a particular warming event directly attributed to an increase in carbon dioxide. And what is seen physically and observationally is well represented in the climate models. So our projections out to 2100 are called representative concentration pathways. So these are basically carbon dioxide projections. They help us simulate how the world changes given different amounts of carbon dioxide. So there are 4 main carbon dioxide amounts or simulations that get talked about. So that's 2.6, 4.5, 6.0, and 8.5. And 2.6 is the best scenario, right? This is where we were in 2000. And RCP 2.6 puts us at about the same point. 8.5, however, is is a very high rate carbon dioxide content. Okay. So the RCPs are related to the global temperature, and we can see that in this figure here. So here's our 2.6 and our 8.5. And this is from the, not the latest IPCC report, but the report just before that. And we've got, this extends from 2000 out to 2400 basically. And we've got our global mean temperature increase relative to 18.
Why don't you consider getting some lunch? What? Where are you?
Sorry. Let's see. I got thrown off my track. I'm sorry. Oh, okay. Yes. Okay. So only the low mitigation goal, right, of RCP 2.6 keeps the global temperature below keeps the global temperature increase below 2 degrees Celsius. All of these others are all over 2 degrees Celsius by 2100 here. And then keep increasing afterwards as well. And so these are model results from projections under the RCP 8.5, so out to 2100. So the global mean temperature is about, what is that, like 4.5 degrees Celsius higher than, yeah, about 4.5 degrees Celsius higher than the global mean temperature in 1850. So we've got temperature modeled up top here and precipitation modeled down here. So as you can see, there's the global temperature increases everywhere. And with respect to precipitation, similarly to the precipitation outlook, blue indicates more rain, and the brown indicates a drying out. So this isn't as clear cut, but taking the global average, you can see that. But if we were to take the global average, global precipitation is actually increased, partially because of these strong signals in the tropics where rain increases. But there's also a fair amount of drying in places that are already dry. So even as global precipitation increases, there will be already vulnerable places that will be inflicted by strong drought. And then in addition to, precipitation and global temperature rise, we also see a global mean sea level rise. And we've got the RCP 2.6 in blue here and RCP 8.5 in red here. So even under 2.6, we will see we're projected to see a pretty significant sea level rise. And here we've got the Northern Hemisphere sea ice extent. And under 8.5, the ice is completely melted, even before 2100. Under 2.6, there's a lot of uncertainty related to that, but it's projected to stop ice decrease around 2050. And then global surface pH, we see that under 2.6, the global ocean surface pH is relatively, doesn't change too much, which is good. Whereas 8.5, we see a pretty drastic acidification. And then just a little bit more about like costs of global warming. that we kind of see like in the IPCC results. More intense heat waves, droughts and fires have costs human lives, infrastructure, ecosystems, agriculture. Warming worsens air quality. Currently, there are already 7 million air pollution related deaths annually. Ice melt leads to sea level rise, leads to coastal flooding. So cities and infrastructure destroyed. And of course, like coastal ecosystems as well. Worsening conditions globally leads to climate refugees. Warming temperatures alter ecosystems, causing species to die out, and the acidification of the oceans hurts shelled organisms, especially coral reefs. So the problem with the RCPs is that it doesn't take into account really human activity. It's they're just what if scenarios where carbon dioxide is kind of artificially added into the system. But human activity plays a pretty significant role, right, in how much carbon dioxide gets into the atmosphere and comes out of the atmosphere. This is from the IPCC report back in 2001, but it's a lot simpler than some of the ones that have come out, and it captures two of the main issues, which is natural flux, right, is indicated by blue arrows, and that's like how many like gigatons of carbon, I think, are added into the atmosphere or taken out of the atmosphere by natural processes. And then we've got anthropogenic flux. That's things like land use change resulting in carbon release, like the change from forest into agriculture. And then we've got fossil fuels and combustion and industrial processes, and that's all releasing carbon dioxide into the atmosphere. So human action must be accounted for, right? Because we can change how much carbon dioxide we put into it, whether it's a positive change or a negative change. Well, that depends on us. And so to account for human action, there are there are simulations called shared socioeconomic pathways. And so these are different ways in which the world might evolve in the absence or with climate policy. And then these different levels of climate change mitigation that could be achieved when the mitigation targets of the RCP are combined with the socioeconomic pathways. And so there's 5 main ones that are kind of like imagining the different worlds, right, that we could be living in the future. We've got all 5 of them on this plot here, where socioeconomic challenges for adaptation to climate change increases from left to right on the bottom, and for mitigation of emissions from the lowest challenges for mitigation emissions to highest challenge for mitigation. So SSP1 has both low adaptation and mitigation challenges. That's because it's the most sustainable world. It's a world of sustainability focused on growth and equality while decreasing emissions and moving towards more green technology. And this is the most optimistic path that we could possibly take. SSP 5 is socially and economically optimistic, but it pays for that with fossil fuels, basically. SSP 2 is business as usual. SSP 3, this is people become more insular. Nations and countries focus less on global issues and more regionally. So policies shift to reflect that. Nations become more focused on their own security and their own personal development. And SSP 4 gap, the gap widens between the haves and the have-nots with respect to countries. So wealthy, industrialized countries dominate, but more vulnerable communities that are impacted drastically by climate change suffer the most. So we've got the 5 different paths here. And we've got projections for each path, indicated by different colors. So, these are the different targets for the different mitigation targets that we saw for the RCPs, with the addition of 3.4. But we've got 2.6 in blue, and 8.5 is in gray. And we can see the net carbon dioxide emissions on the axis here, and the resulting global temperatures are indicated by these red bars here. So SSP 5 under the 8.5 RCP, the baseline, we don't do anything while we try to fix the world, basically, ends up being one of the worst in terms of carbon net emissions scenarios that we could have. The best scenario, of course, is SSP 1, the sustainability path under the very tight mitigation goal of 2.6, and that would actually drop us down to the point where we're actually sequestering emissions. Anyway, so in conclusion, talked about how order and chaos gives us predictive power, and we can make reasonably skillful predictions of weather and climate, like in seasonal outlooks, despite there being a gap in predictive skill. We're confident in the 2100 projections of global temperature, sea level rise, and precipitation as a result of carbon dioxide rise, and how the global community acts within the next decade will be a deciding factor in the ultimate cost we pay. And then today, COP27 ended, and I saw an article about it, and it seems like, in general, they didn't really talk about too much, or specifically, they talked about a lot, but they didn't really decide anything new. So the one big resolution that came out of all this was that they wanted to start a fund for communities that are vulnerable to the effects of climate change. But who will pay, and how much this fund will be, and who will it go to all seem to be issues for next time. And they didn't resolve anything regarding mitigation or downsizing fossil fuels explicitly. And just in general, the negotiators at the press conferences all seem to be pretty tired. And who isn't? But we still have some time to turn this vote around. We can do it. We got this. It's not really any other option. And yeah, that's it.
Mary, this is Bill Sweetlick. Thank you very much. Is your presentation reflecting the work you're going to be doing for your dissertation or have done for your dissertation? And will this be some of the work that you'll be defending at George Mason?
No, actually. I'm doing a little bit here on pushing that, closing the gap. But I didn't talk about any of my own work here.
Okay, interesting. Maybe to clarify for the folks listening, can you explain what the IPCC is?
Oh,
And then
yeah.
after you mention that, can you talk a little bit more about the RCP, the 2.0 to 8.5 RPCs and what those reflect?
Yeah. Okay, so the IPCC is the Intergovernmental Panel on Climate Change. It's the it's a UN it's a UN like committee. I think I'm not really sure on the actual word, but it's basically like a global effort to consolidate scientific information regarding climate change into reports that policymakers all over the world can read and use to inform their decisions. And it's a very time-consuming process. Everybody has to they go through and they make a draft, and it's a very long report. And then they take each chapter of the report, and they take each page, and they sit down together in a meeting, and they go line by line, and they say, okay, does everybody agree with this sentence? No? Okay, let's get a committee. The committee is going to talk about this sentence. And then they're going to decide how to word it so that we can all agree on what's being said.
And so they're coming to consensus on what the climate science is saying?
Yes, absolutely. Yeah. No IPCC report gets published without the consensus of basically every nation in the UN.
And then the RCPs that you have up there on your slide, once again, can you explain those a little bit further?
Yeah, sure. So so they represent I'm trying to think about. Okay, so I guess like the level of emissions that are allowed. So the higher the number, the higher the level of emissions each year. So under 8.5, more emissions are emitted. It's kind of like continual growth of and business as usual almost of various, like fossil fuel carbon dioxide emitting industries and human activities. And RCP 2.6 and 4.5 and 6.0 set our projections under the assumption that we have set certain limits for how much carbon dioxide we're emitting. So 6.0 is kind of like the least amount of restrictions that they've modeled. And then RCP 2.6 is more optimistic. We've gotten our carbon dioxide emissions down significantly.
Where would we stand now as a baseline? If you could draw a RCP baseline current human behavior.
Yeah, last I understood, we're on track for 8.5.
If we don't change what we're doing in organizations like COP27 and all the other negotiations don't come through with more stringent reductions of CO2, we're on an 8.5 pathway.
Yeah. At any given point, right? Like we could implement mitigation strategies, but unfortunately, it's very time sensitive. Once we reach a certain point, we'll have say, I think it's 2025 or 20. People are aiming for 2025 because the sooner we start mitigating, the better. But I think it's somewhere around 2030 is the tipping point, where we'll already be at a certain level of carbon dioxide. That means that the warming will be pretty drastic.
Thank you. Any other questions for Mary?
Yes, I have one.
Hmm.
So if, Mary, if you were a baby boomer looking to retire somewhere to avoid fires, drought, extreme weather like hurricane and blizzards,
Hmm.
what part of the country would you go to?
Let's pull up oh no, it looks nice. I would say definitely not somewhere on the coast, because most likely, well, I don't know. Yeah, I don't know. The morbid answer is, how long are you expecting to live? Because I mean, I wouldn't go anywhere too close, too near the coast right now. But if you know, like you could probably get somewhere like, I don't know, like a mile off the coast in some places, and you know, when you die, you can leave it to your kids, and they'll be able to sell it off as a piece of prime shore property.
Yeah, I just read an article about these two retired physicians.
Mhm.
They have a home in Half Moon Bay, which is near San Francisco,
Mm.
and a home in Florida.
Mhm.
Of course, in California, they were getting smoke from the fires, and in Florida, they had the hurricane. So they did some research, and they ended up picking Asheville, North Carolina, as the place to go.
Oh, it's not too bad. I'm just looking at the preset here. Yeah.
Yeah, look, Mary, looking at your maps, I was thinking staying right here in Fairfax. Doesn't look too bad.
Exactly, Virginia looks good.
Yeah, I was also thinking that. I was like, oh well, like on the East Coast isn't too bad. Like we'll get a little hotter. It's very possible that by the time we get to 2100, we won't have cherry blossoms in the winter anymore
Hmm.
because they're very reliant on
I don't think I'm gonna be around in 2100.
well, so enjoy the cherry blossoms then.
Barry, just another question for you. Back in 2006, of course, Al Gore came out with his movie Inconvenient Truth.
Right.
And in that movie, he showed a number of slides that kind of looked like some of the temperature and precipitation change slides that you're showing
Mhm.
based on your models now.
Mhm.
And back then in 2006, if I remember correctly, those slides that he showed, things kind of look the same, that basically weather changes, climate changes would be quite erratic all around the globe. Some places would really be severely changed and impacted, and others would be lesser so. Is it safe to say that these newer climate change models are basically predicting the same thing that was predicted by the models back then?
Yeah, in terms of basic temperature, I would say so. Yeah. Well, but I mean, at least with respect to temperature, Syukuro Manabe in the 1970s predicted basically this same thing, and he won the prize for physics, the Nobel Prize for Physics, just last year or the year before for it. Like just because it was such a seminal discovery that we're finding again and again is true. But I'd say that the models now are probably better, just in terms of even just in terms of like the amount of data that we have. So even though globally, right, the pictures look very similar, the how regions are impacted, is going to matter more to the region than kind of a global picture. And regionally, our models have improved a lot.
Okay, thank you. And then one last question from me, and I see we're getting almost to 1 o'clock here. On the shared socioeconomic pathways, that kind of gets into the question of what do we need to do to get this climate change, global warming situation under control? Did I hear you say that SSP2 right there in the middle of your chart is kind of the status quo if we don't do anything more than what we're currently doing? That's SSP2?
Yeah, that's assuming, right, that that's assuming that like we don't do anything, and we don't I think it's like we don't necessarily focus too much on sustainable development of technology or alternative fuels or and I think probably that like we don't neither are we like systematically trying to use more fossil fuels either.
Mary, I think there's a question for you in the chat.
Yes, Kathleen says, do you think our U.S. coastal areas will be underwater in our lifetime? I think that it's definitely possible that some areas will be underwater in our lifetime. It's very like locally dependent, right? So on like how flat the area by the coastline is. But most likely, I mean, even now, right? Like we're seeing flooding issues in coastal cities. I know New Orleans has had like some serious flooding related to the rise in climate and excuse me, the rise in sea level as a result of climate change. Backed also by the fact that they're kind of on a swamp and they keep pumping out the water, but every time they pump out the water, they sink further into the swamp. But I mean, even here, right? I think Ellicott City has had some serious issues with flooding. And I think Annapolis as well. Yeah, does that answer well enough? Okay.
Yes. I was thinking of like areas like Virginia's Eastern Shore and Delaware, they're flat and low. I was assuming that they'll have more flooding.
Yeah. Just looking at this picture here, right?
Recording in progress. That doesn't work.
So yeah, so if there's any areas by like 2100 that are, like lower than about 0.4 meters, it'll probably be underwater. If nobody does anything. But I know that there are also a lot of efforts, to basically build up beaches, shore up beaches, if you'll excuse it. Well, I mean, like taking sand and sediment from elsewhere and dumping it onto the beach and trying to, help prevent erosion. And I know they do that. In Hawaii, they have they've built stone walls.
Yeah.
Yeah, but I would say like definitely coastal areas are at risk.
Yeah, because I have mine. Yep.
Somebody's mic is on.
Yeah. Ah! Sorry, guys. Trying to get.
Let me.
I just signed in.
Okay, thank you, Roland. Roland says that Smith Island is projected to be underwater by 2100.
Linda, if you have a question, if you can move away from Debbie, if you have a question, that would be better, because if you are too close, it's gonna make the echo.
Yeah.
If you are too close. Let me unmute you. So it seems you have a question, even though we are close to 1 p.m. Oh, it's already 1. Okay. Yeah,
Okay,
yeah.
I'm now in the choir room instead of the
Okay.
other room.
Okay.
I just was, as a young person, do you see any positive way forward? I mean, I keep thinking maybe there's a tipping point with corporations, we're a capitalist society. Is there a tipping point where people start to believe that this is happening? And I mean, I realize we only have 10 years, but where it becomes, a flood in the other direction. I mean, I'm hoping. Any thoughts from your young perspective?
Well, this is something that I flip-flop back and forth on, because like a lot of people talk the talk, but then something like COP26 and then COP27 happens, and you see people agreeing like, the people who have the power to do things agreeing, yeah, let's do this thing. But if they either they don't agree to enough, or they agree to enough, but they don't enforce it. And at this point, it's like, how much more can we actually do to, I mean, like global, it's a global issue, right? There are a few key, like, I mean, the US, right, is one of the biggest contributors to carbon emissions. So currently, I'm hoping that if we can get the US on track as a nation, and not just individual states, but as a whole on track towards severe carbon reductions and carbon sequestration and improved technologies, that hopefully the rest of the world would follow. Yeah.
Mary, I have a question for you. What is your prediction for our winter weather in Virginia and Fairfax here this year? I just heard Doug Kammerer on NBC4 give his prediction for the winter and wondered what yours was.
Oh, I mean, I wouldn't know personally, but I would probably go by, like this outlook that the Center for Climate Prediction did. So probably warmer temperatures, like, and average precipitation.
Okay, well, that's about what he said.
Okay, yeah.
Maybe low on the snow, but yeah, a little
We can do
warmer
it
than
snow,
usual.
I think somebody.
There's a question in the chat. Yeah.
Yeah. Okay. How real? Harry says, how realistic is SSP for inequality? The results appear to be similar to the green approach, however, requires the have-nots to carry burden. Yeah. And then Kathleen said, yes, Harry, it sadly looks like the have-nots bear the burden. Yeah, that's kind of that feels like the track that we're on right now, honestly. I was just we do kind of a current events discussion in the department once a month, and we very recently were talking about the climate related flooding in Nigeria, and it's really tragic what's happened there. And the Nigerian government says it's an emergency, but it's not a state of emergency. So nothing's really being done there, and they're not responsible, right, for the vast majority of the carbon emissions. But yeah, and I mean, we'll see that we'll see the burden being borne unfairly, not just on countries that aren't contributing to the crisis, but also on on disadvantaged and vulnerable populations, like in first world countries, just as an example, we're going to be getting a lot of heat waves up in the northern part of the country, but people there don't have air conditioning for the most part, because climatologically they've never needed air conditioning except for maybe 1 or 2 hot days, but the hot days are going to get much hotter and more intense, and they might not be able to afford to have AC for those like 1, 2, maybe 3 or 4 days, where at least to their mind, right, that they would need AC, but that's the heat is still dangerous, and so that would result in that would result in like an increase in heat wave related deaths in the northern part, particularly in disadvantaged communities.
Bill? I don't know, I mean, you have any last question? Because I know it's already 1:10.
I don't have any further questions, and I really would like to thank Mary for the presentation. I thought it was very enlightening, and good to hear that she has some positive thoughts about what can be done and where we can go with all of this, especially from a young person who hopefully will be around in 2100 or longer.
Thank you so much, Bill. Thank you so much, Mary, for this wonderful presentation. Yeah, now we can see everyone. We can see the squares. Yeah, let's give a round of applause to Mary for this wonderful work. I know you have your camera turned off. You are up. You are, giving. Yeah, Chuck. Thank you, Chuck. We're glad that you are here. So.